I'll get rid of this. All right. So, all right, so here's the stuff you want in a forensic disk duplication solution. You want to make sure it copies all the data, and it's a forensic duplicate of the original medium with every bit on it. And if it encounters read errors, you want it to do something sensible, like print a message and store something in the log file that tells you had read errors, so you're not just guessing. Some of them will put a placeholder in those blocks, but somehow it should handle them in some intelligent way so you will know there are read errors and know where they are. It, of course, should not change any of the evidence while it is acquiring it, and it should be verifiable and repeatable. That's the plan here. Now, of course, if you have bad sectors, you won't be able to repeat it because bad sectors come and go. But if you don't, you should be able to get multiple images from the same drive and get exactly the same answer right down to the MD5 checksum. That's where the whole thing started, that forensic, computer forensics was considered to be a perfect mathematical scientific activity as opposed to other kinds of forensics, because we had this perfect reproducibility. All right. And of course, like I said, it doesn't really mean you get every bit on the drive. It means you get every bit that the operating system can see on the drive. Now, it is possible to adjust the drive starting block so that part of the drive is reserved, excluded from the operating system's configuration, and they call that a host protected area, and it's used for things like drive firmware. So it's an issue. Now, when you're done, you end up with a forensic file, and there are various kinds of formats. The types of images, though, not to need file format yet. The type, you can either do the complete disk, which is the standard and probably the best to preserve all the evidence, or you can do one partition. Drives are partitioned. Now all Windows machines have a separate boot partition from the system partition, and most commercial laptops have another partition that has an image used to restore the operating system in case you foul it up. And so you might image only just one of those partitions. And then there's logical gathering, which is when you get anything less, like just a file, just a folder, just the folders of a certain time range, just the folders and files owned by a certain person. And in that case, you're not going to be able to retrieve deleted data because you're only going to get active data, which is files that are in use, and you're not going to be getting the unused sectors between them because those are not in the directory and they're not owned by anybody and they don't have any timestamps, so they won't be included in any logical category like a folder. So a complete disk image, here's what you have on a disk. You've got a boot sector, which is 512 bytes at the start. Then you have a partition someplace that the original equipment manufacturer has used to store an image so they can recover it by pressing some function keys during boot up. Then you might have a partition 1 and a partition 2, like a drive C and a drive D. And you could make an image of just one partition, but the general thing you try to do is just get an image of the whole drive, because then you've really got it all. Then you send that to prosecution or defense, and they can both chew on that, and they've got all the data. That was the idea. Yeah?
Sorry, I missed, what was the host protected area again?
The host protected area is an area that the operating system cannot see. It can't store any files in it, and it can't read any files in it, but the drive controller can. And so it might have things like firmware versions.
Okay, so it's like a part that the hardware hangs onto it for itself.
Yeah, and like internal configurations. And you could hack the firmware to read and write into that area if you wanted to, and you have to be a sort of that level of hacker. Travis Goodspeed does this, and various other people have done it. I used to do it back in the days of the Commodore 64. This was a common copy protection scheme, was to put an essential part of loading a game in the area that the computer can't see unless you hack the firmware. So it's possible, but it's not common, and only pretty advanced users would know how to do it. You could hide some files there, though, and they would not be captured by most forensic tools.
When you say
Yeah.
imaging, it means duplicate, copy, or
Imaging, what? I didn't understand the
when you
question.
say imaging with
Yeah.
computer, would it mean copying,
Yes.
duplicating?
Yes, but they call it an image because you copy every bit and put it in a file, like an image file. That's what they call it. A .img is what it is in the Mac.
So in the corporate world, in the company, when someone gets offboarded, they
Yeah.
do the imaging.
When
So
someone
they
gets what?
They do imaging of the computer.
Yeah, that's another issue. That's like the kind you might have with Norton Ghost. You'll have an image that you deploy. That's the kind. A deployment image is not a forensic image, because if I have computers with 500 gigabyte hard drives and I'm deploying Windows, my Windows is probably only like 20 or 30 gigs. So the image that's deployed from an image server, like a Windows deployment server, is only 20 or 30 gigs in size, because I only write the files I need, and I don't care what's on the unused part of the disk. But a forensic image is the whole thing, including the unused part of the disk. So if you have a 500 gig drive, a forensic image is 500 gigs. And that's not what you want to deploy, because you usually only want to make the operating system work. You don't really care about the unused part of the disk. So by the way, you can use Norton Ghost to make forensic images. You use a -I command line parameter, and then it will make them. but that is not its normal mode because most people don't want that. It's a very important difference. The normal disk image is actually a logical image. It's only the files that you need in a certain file tree. It doesn't have bit by bit every bit on the drive. It just has a tree structured list of files to write to the drive.
But
Yeah.
doesn't the company need to track, like, after they offboard someone, and in the future something appears like
Oh,
that,
you
like,
could.
in order to investigate, wouldn't it be easy to...
This just depends on how sensitive your work is and how worried you are. You're right. You might want to make a forensic image of a machine after firing when somebody leaves, so you have evidence of what they were doing. I guess if you were handling military secrets or something, you might do something like that. But in general, they mentioned many times in this book, a lot of companies make procedures like this, and then it turns out that they just have a giant pile of stuff that nobody has time to go through. So it is kind of pointless to collect something if you really don't have time to look at it. But if you had like somebody auditing you that wanted to really go down and say, what did you do with all this stuff, like happened to Hillary Clinton, like years later people want to know all your emails, then you might wish you had done something like that. So you really had everything. Anyway, so FTK Imager, we used it before to get RAM images. It'll do these other things too. It'll do a whole physical drive, a logical drive, which is a drive letter, typically a partition, or an image file. You can open an existing file, or you can get the contents of a folder. If that's a logical acquisition. All right. And then you can choose the image type. A DD is what the Linux DD command creates. It is just a bit-for-bit copy. So if I have a 500 gig file, 500 gig drive, it will be a 500 gig file. No compression, no nothing, no extra data, no hash, just a copy of every bit on the input medium bit by bit. That's what DD creates. These other formats are intended primarily for Windows systems, and they're all compressed to make it smaller. I think Smart is compressed, I'm not sure. I haven't used Smart, but E01 and AFF are very common. E01 is the expert witness format that's used by Encase, which is the standard for police departments, and AFF is commonly used by FTK Imager, which is the standard for the FBI. And they're both big commercial products, and both of them will take essentially a DD image, and then they will compress it with zip or some similar function, and then they will break it up into little chunks, typically 1 or 2 gigabytes in size, because a lot of removable drives do not like handling files that are bigger than 2 gigabytes. So it's convenient, instead of storing one 500 gigabyte file, to store a whole bunch of little files that can be more easily copied and moved around. And then it will attach to them metadata, like the hash of all the forensic hash to make MD5 or SHA-1 hash, so when you make a copy, you can tell whether it's an accurate copy. Yeah?
Which imager do we use to not alter the system?
That's a very important question, and the Imager software does not control that. This Imager here, the problem is when you alter the evidence, when you connect it to a computer, it's when you boot up the computer that changes the drive, before you get a chance to run any software. During boot up, the drive is mounted, and it's given a drive letter, and the operating system touches it, and it changes the date on the recycle bin, and it puts journal entries in the journal. So it writes, during normal boot up, every operating system wants to write on every drive. And so you either have to get a special forensic drive operating system like DEFT that has been modified not to do that, or you have to use a hardware write blocker. And then you'd use a tool like this. But this tool does not protect the drive at all in itself. It trusts you to have protected the drive at the level of the operating system or the hardware underneath it. That's really important. There's no software product that runs on an operating system that can protect the drive because the damage has happened before that.
So what happens if you use Windows Restore, and then right after you have it in?
Oh, System Restore? System Restore is not a disk image. It does not do any, it doesn't even fix all the files. It doesn't even fix the metadata of the files, which is why you can't use it on Windows servers. But even if it did, it's not going to restore the slack space, the gaps between files. It's only going to restore the active data. So a restore point is not a forensic image. It's just like another kind of backup. So all it has is the files that are in use. So it's not really rolling the clock back 100% to make the way the disk was in the past. It's just taking some system files and rolling them back.
I meant if intruder used it, can't we?
Well, if an intruder uses System Restore, yes. If they do something bad and then they use System Restore to hide the evidence is still there. For like deleted files. Reinstalling the operating system doesn't get rid of it. Reformatting the disk doesn't get rid of it. Defragmenting doesn't get rid of it. Each of them shoot some holes in the evidence. They write on some parts of the disk. The only thing that will really clean a disk is to write fresh data on the whole platter. And you can do that from the command line, command disk part. You do select disk and then clean all. That will write zeros over the whole drive. If anything less than that doesn't necessarily get all the evidence. And in practice, all these system maintenance tools like System Restore are designed not to waste any more time than necessary, so they make no attempt to write to the whole platter. They try to write as little as possible to get the job done, so they don't really clean up much in the way of leftover evidence. Yeah?
What's bleach bit then?
What's what?
Bleach bit. What is that?
Feature bin?
Bleach.
Bleach? Oh, bleach. I think bleach is one of those tools that does write zeros all over the disk. I know eraser is, and steganography is. There's a bunch of tools you can download that will do it. You don't really need them. You can do it from the command line, but it's important. And in the Mac, you have an option right in disk maintenance, disk utility, to clean the drive. These are good questions. By the way, drive manufacturers often put a disk cleaning utility in the firmware of the drive, and you can send it a SATA erase command. And what I have been told is experts don't like that at all, because in practice it fails fairly often, and you can't test it. Once you erased it, there's no way to do reads to see if the data is still there. So anyway, another issue, by the way, I may have mentioned before, this is something Kyle Rankin did. Kyle Rankin's a Linux expert. He gives talks here now and then, and he had an issue. What do you do when you have a cloud server, like an Amazon virtual machine, and you've got your confidential data on there, and now you're done with it? Now, when Amazon E2C was new, they actually forgot to clean the drives. Somebody bought an Amazon instant, put on a forensic tool, imaged it, and found all the last guy's data on there, because Amazon didn't think of this. So you don't really know if Amazon is cleaning it. But suppose you have something like PCI or HIPAA compliance, where you have to testify, I made sure that we didn't leave some copy of this data floating around. What you need to do is you need to stop using the drive, mount tools in RAM, and then run tools from RAM to erase the drive and tools to verify that it's erased. And he had a procedure to do that, which was pretty cool. Before you tell Amazon you're done with it and they can have it back, you make sure you really cleaned it. Yeah?
But Amazon's like rotating all the machines, so just because everywhere that you can touch you've erased it from doesn't mean that they should be totally wiping disk, but
That's another issue, right? What does Amazon have in the way of backups and server clusters and everything? I know Amazon does have a HIPAA compliant option. If you pay them more money, they will do something and swear that they've handled that. Azure, I think, will not yet. Last I heard, it was about a year ago, Azure said, we can't even promise you what country it's in or how many copies or anything. If you're worried about that, don't send your data to Azure. But they might have improved and had some kind of higher price Azure option that really controls where your data is. Yeah.
because all that stuff is automated, like just
Yeah.
like they have like a server that kind of is managing the herd and
Oh,
the
yeah.
slaves and the masters, and like it's just promoting and demoting and re-imaging and resending out, and
Yeah.
you know, if that breaks down in some way that they don't notice, then
Yeah, I know. Another option might be to put your data up there all encrypted and don't put the key up there. And then if they're storing it around, you have another layer of defense. But that probably wouldn't be practical with people doing searches on databases and stuff. It is a big issue. This is why a lot of people prefer a private cloud, where you still have your own data centers, your own machines, and everybody connects to them over the internet. But then you know where it is. You know how many copies there are. Those public cloud services, you got to ask. Anyway, so here's the host protected area and another thing called the device configuration overlays. These are just ways to reserve part of the drive for the controller to use that the computer will never see. And so you can hide rootkits there. You can in principle hide any kind of data there if you alter the firmware. But if you aren't sophisticated enough to be hacking the firmware, then you can't read or write that area, and that's what most people expect. So active data is the only data we normally see. This is data that is in the tree. You can open Windows Explorer and go to C and open a folder and see a file. That's all active data. Data that's in use, that has a file name, an owner, a creation date, a modification date, and a list of sectors. And when you delete a file and empty the trash, it's removed from the directory, and it's no longer owned by anybody, it no longer has a creation date or a file name, but the data is still sitting in the clusters because it just is more efficient to not bother erasing them. Due to the physical properties of the magnetism on the hard drive, it is just as fast to erase it and write at the same time as it is to erase and then write later. So it's a waste of time when you delete a file to erase the clusters. It'll just write over them with the fresh data. This is not true of SSDs. SSDs are much slower to erase. So in fact, there's a background garbage collection on SSDs, finding blocks that are not necessary and cleaning them so you can use them later. And so latent data, the latent data, the other two categories here, does not last as long on modern SSDs, but some SSDs are used in inefficient ways, so they act just like hard drives, because the operating system does not tell the drive controller when it deletes a file, so it is unable to do garbage collection because it doesn't know what's being done. Anyway, so the largest part of data that you get from slack space is unallocated space. These are whole clusters that are no longer in use. and they're just waiting for someone to store a new file on them. And you often find that if someone had like a Word document or image, the whole thing is still there because they have a huge drive like 500 gigabytes and they haven't come anywhere near writing on it yet. So all the clusters are just sitting there right in order. The only thing you've lost is the file name and creation date and the owner, but the image is still there to reconstruct. That's what you typically get. There's also a much smaller, less important kind of data, which is file slack. The drive is used in 512 byte sectors, and the sectors are typically allocated in larger clusters, like 4096 bytes. So if you store a file with maybe 300 bytes in it, it has to use 4096 bytes on the disk because that's the smallest allocation unit that can be given a file name. So in that case, you store 300 bytes, and there's almost 4,000 bytes of old stuff left at the end of the file that you didn't write. That's going to be not a whole file, it's going to be a fragment of a file. So that's what's called file slack. Little bits left at the end of the files. Typically that's got to be in a normal drive less than 4,000 bytes. And it's always missing the start of the block, which is where you find things like the file header, so it's pretty hard to get any good out of that stuff. So it's not really so practical from a standpoint as a forensic examiner is going to find something in there you can use. It's more an issue of if you're going to throw away a computer and you want to swear to court that I made sure nobody got the social security numbers of my customers. Well, there could be a few social security numbers hanging out there and you'd wish you want to make sure you cleaned it. Anyway, so you can do a partition image if you want to. This is not normally what anybody does because you might as well just image the whole hard drive if you're going to go this way. But if you do, you would get all the allocation units for that partition, including the deleted files, so you might be able to recover some deleted files. You might not get them all, but you have some chance of getting them, but you won't get unpartitioned space on the drive, host protected areas, and other partitions. A logical image is where you do a normal kind of backup. You back up everything on C, everything in C documents, something in a folder that's only going to get files that are in use. It's not going to get any deleted files, but this is what most people do all the time for backups, and that's fine. It does preserve some data as long as you know what you're doing and why you're doing it. Maybe for some reason you don't care about the deleted files. We'll have several examples later why that would come up. Here's some examples now. You might have a shared drive, shared by many people. And if that's true, you might have a court order that gives you authority only to collect the data owned by one person, who's the suspect, and you're not allowed to go collecting all the data about the other people who are not part of the case. And in that case, you've got to forget all about getting deleted files and slack space because you can't tell who they belong to. So you cannot show that they obey the limits of your court order. So in that case, all you'd get is the active data that has an owner set to the owner I'm supposed to be investigating. That's the only thing you can do. And that's typically when you have RAID volumes, network attached storage, storage area networks, big storage units that are shared by many people. Another issue is you might have a storage device that is in current use and they are not willing to take it down for duplication. To image every platter, you'd have to take it down for a while, go image it for hours, and they might not be willing to do that. They might say, do something that you can do while it's running that doesn't impair business, and we will settle for less perfect collection of data because it's more important to us to keep that device up and running. So that's an issue. Another option there is a live image. You can connect over the network while it's running, and you can copy the whole drive while it's running. That can be done, but often it's not practical for large storage arrays because you don't want to slow them down, and they run some screwy disk format that's hard to understand anyway. And it's really too much bother to get the whole image and try to figure it out. What you really want is just the files. Like I said, that's what I ended up doing with this supposedly stolen Mac. I was not able to get a real image of the drive. I wasn't able to do much anything except just query the real file system for the active data, and I settled for that. That was easy enough to do, and it got me some evidence. You're always balancing how much evidence do you need against how much bother is it. Here, so a logical image. You don't just copy files like a backup, though, because if you copy files like a backup, you typically lose the creation date. If you just copy them by dragging them onto another volume, their creation date will be the date you made the copy, not the original file creation date. So if you use FTK Imager or Encase, it will copy all the files in the folder with their metadata, not changing the owner or the timestamp or anything, keeping it all there. And then it will put it in a container file so you can have a hash value for it. The hash value is very important so you can make copies of it later and you can verify that those copies are accurate. Normal backup tools don't do that. You make a Windows backup, it's just a file, it doesn't have a hash value because they are not expecting you to make multiple copies of that. Okay? And so that's why these forensic tools are more useful than just a simple backup utility. And then, of course, there's non-standard data. You're going to get data that did not come to you through a proper forensic process. This is true of any investigation. Somebody just hands you a USB drive with evidence on it. Well, you didn't collect that with a forensic tool. You don't really know how they put it on there, and yet it's not nothing, it's something. So if you get evidence like that, then all you do is record who gave it to me, what condition I got it, and then you preserve it from that point forward. That's the way it always is. If you go to a crime scene and find things lying around, you don't know how the data got on them. You take them the way they are, you record, here's what I found, and from now on, I'm the professional, from now on what I do will be recorded properly, but whatever happened to it before I got it, I don't know. And so there's lots of things here. People can give you files they got various places. And if you make some kind of mistake, or if you have to do something sloppy for some reason, like an emergency, or you don't have the right equipment, you always record what you do. I think I mentioned before, one simple case is a cop went to a crime scene and found a cell phone and wanted the instant messages. He didn't have any equipment, so he just paged through the messages and took photographs of the messages. That's evidence. You can argue that it's not a perfect procedure, that it alters the evidence, that it doesn't get it all, but it does get something. The real evidence is the human testifying. I went there, I picked up the thing, I saw this stuff on there. That's the evidence, is the credibility of the human. It's not the technology. The only reason we use the technology is acceptable is because the credible expert convinces the jury that you can trust this guy, and when he used whatever this complicated script was, he knew what he was doing, or she. Anyway, that's the game. All right, so that's image integrity. You try to everything you collect, you want to put a hash value on it so that if you make a copy of it later, you can verify that it hasn't been altered. And if you have a drive that is failing with bad sectors, it will give you a different hash every time you image it. This is also true of SSDs that are undergoing garbage collection. The data is evaporating while you're imaging it. So when you take another image, you get a different hash. That doesn't necessarily mean you did anything wrong, so you just should be aware of that. It's also true, of course, of any live collection, where you're collecting data while a machine is up and running without a write blocker. It's changing the drive all the time. Things are happening in the background like defragmentation and drop boxes, putting stuff in, and network connections are opening and shutting. It's constantly changing. So if you do two images, they are not going to have an MD5 that matches. So that doesn't mean it's wrong. You just need to understand what you've done and be able to explain it clearly to the jury, why you did it and why it's okay. So AFF is access data, the advanced forensic format. Expert witness uses this EWF format. Just give file names E01, E02, like at the bottom. Both of them automatically store hash values. In case even stores several hash values for parts of the data, including the whole data, and they make typically split the data into a whole series of files, E01, E02, E03, just to make it easier to store and move around. Yeah.
Use the hash for each single small file?
Yeah, it discusses it in your book. It's kind of interesting. I think it does something like break it into blocks of 64 blocks, and then put a separate hash on each one of those. So I don't think it's tied to the file size, but it does store not just one big hash for the whole thing, but little hashes for segments of it, which is probably a good idea in case you get some damage to it later. You can still recover part of it or something. And DD files are created with the Linux DD command or with modifications that can do a little bit better. And all this does is just a direct copy, bit for bit, into a file. That's it. Input device, output device. You can use it to duplicate drives, although it's very inefficient because it does duplicate every bit on the drive, which is far more than you need, for example, to do a ghost image. So if you had a Windows install that was 30 gigs and you used DD to put it on the drive, it would work, but it would put 500 gigs of data on the drive. It would put the 30 you want, followed by 470 gigs of garbage you're not using, but it'll just faithfully copy every bit. It doesn't do any compression. It doesn't add anything to it like a hash value, because that would be altering the data. So the digital forensics groups have made modified versions of DD, like DCFL-DD from the Digital Computer Forensics Lab, that gives you some error messages if it finds bad sectors, which DD won't, and it gives you a hash. Puts it on the screen and it can store it in a second file. You've got the original image, which is just DD, and then you got another file that has information in it like hashes and the date of capture, which is the kind of stuff encased in FTK formats would store directly, but here it has to go in a separate file because the DD file has to be just a copy of the drive but nothing else. So that's the thing. You got to have documentation someplace, so you get hashes and you write them in the pieces of paper that go in your chain of custody. I got the image, I stored it in the original and safe. Here's the image, here's the hash value, so that we know exactly what I got and I can tell it from all the other ones. All your documents are going to have that hash value on it to make sure you're absolutely sure which file you're talking about. All these forensic images are the same in their content. It's just like having a file and zipping it or encrypting it. None of these change a single bit of the contents of the file. They just mean you have to go through a different process to get the contents. So you can convert every forensic format to any other forensic format, but it's typically a large file and a slow process taking hours. So Windows tools typically like expert witness files. That's what they expect because people pay for Windows software like FTK or Encase, and that's what they expect to see. Open source tools typically want DD files. because they're not interested in the Windows compression utilities. And if you want to do something like try to reconstruct a RAID from images of all the platters, which is going to typically require a custom tool, a special tool you purchase, or perhaps even custom scripts you write, then in any case like that, you probably just want to start from a straight DD file. There's no point having it compressed. In addition, all the other difficulties you're going to have trying to put the stripes back together. Yeah?
Well, with the RAID drives, how would it, so would you have to make the DD file to another RAID drive so it matches it perfectly, or
That would be one way, would be to find identical hardware and image it there, but typically you don't have that option. And typically your forensic software doesn't have the right driver to understand it. So what you have to do is examine it and figure it out. That's why it's painful and a lot of work. Because RAIDs not only have a pattern of storing a stripe here, a parity, stripe, stripe, they also have typically proprietary formats they don't tell you to store it on there. So each brand is different. So it really is quite a job to dig deeply into a RAID. And that's why I say most of the time it's just not worth it and you just do a logical acquisition. But if you really had to, for example, Drive Savers totally does. All the big cloud services go to Drive Savers with their gigantic arrays. So they get crashed and we lost all the data. Drive Savers told me last time I visited them that it's very common that this giant array of 20 drives has 2 or 3 drives all fail at once, which violates their planning. And they take that whole thing in and they pay them a pile of money and they will really figure it all out, like you're saying. But that's real expensive, because you have to be able to know all the secrets of all the proprietary formats. It's basically a job of reverse engineering, and that's all they do there. And all their staff gets like 2 months of special training a year, learning all the latest tricks. And you got to pay a lot of money for all that. Most investigators are not willing to go to that much work to get every bit of data off the device. You don't really need to get the job done. But if you ever do, I would just outsource it to Drive Savers before I would try to figure it out. Anyway, all right, so I got a few iClicker questions. Come grab one if you need one. Looks like there's a few out here, and there's more underneath those envelopes if they run low. Let's find my software. All right. Okay. All right, so my base frequency code, Duffy might want that. Anyway, all right, what's the hidden part of a hard disk? All right, looks like I can quit at 30. I'll wait till 35. I see some answers still coming in. Okay. All right. And that is the host protected area, the last one. Good, a popular answer. All right. Which one will let you recover some deleted files? Okay. I'll quit at 30. All right, and that's the point of a forensic image. You have every cluster, including the unused clusters, and some deleted files can be reconstructed from the clusters. Some of them are really gone because they've been overwritten, but you get some of them back. This is why the first thing you do is if you have a system with evidence on it, is you stop using it, because everything you do with it destroys more data. So you're just making it worse by using it. You want to make a copy of it quickly, rather than messing around with it. All right. So what kind of acquisition has the best chance of recovering deleted files? I'll quit at 30. All right, and of course, the whole disk is the best chance. Partition has some chance, but the whole disk is what's going to give you the best chance of recovering the most deleted files. All right. What kind of acquisition can ensure that you only get files owned by the suspect? I'll quit at 30. All right, and this is logical acquisition. You can only do it with active data. This is, of course, what the entire flack is about the NSA. They were always been allowed to target and investigate one person, but they're just scooping up everything, including people that they have no probable cause for, and that certainly would appear to violate the Fourth Amendment. Anyway, all right. So what kind of image is most likely to be accepted in court? I'll quit at 30.
The last answer would mean they would all be acceptable, or they're identical in their identical formats.
In this respect, they're all the same. They would all be accepted.
Okay.
All right. I'll quit at 35. All right. And of course, that's the point. They're all mathematically identical. The mathematical transformation will turn into the others, so they're all the same as long as you explain it. The EnCase would like you to believe that theirs is accepted just for being EnCase, but it's really accepted because your evidence, your expert is credible. And experts that prefer to use Linux tools succeed just as well with their unusual formats, because the jury doesn't know or care what the industry standard in this business is. They just look at the expert and say, does this expert seem to be credible? Do they seem to have done something sensible? And it's the human credibility is what matters. It is not the tool. Unless you use a defective tool and the opposing expert can actually prove there's something wrong with your tool. That would be a problem. Anyway, but none of them are perfect. They all have bugs, just like all computer software. So anything that matters, you should verify it with two tools. What I always did was use something I had and then verify it with a raw hex editor like HXD. Just go look at the raw binary to see if it's really there. At first couple of times, tools totally lied to me. I really freaked out. I was really upset when the tool I used called ProDiscover would just completely get the wrong answer for important things. And I said, man, I wonder how many people are in jail because of this tool. And I remember my teacher said, never trust your tools. Always check anything important with another tool. And then, that's your answer. You say, it doesn't matter what tool you use, any competent examiner will find the same thing because it's really there. And I verify everything with multiple tools. That is the right answer. Anyway, all right. So which image is easiest if you're using open source tools? Easiest to use. All right, looks like I can quit at 25. All right, and that's of course DD, just a simple image with no compression or anything. Makes it easier for the tool to find the data. All right, let me just stop this recording, which I think might have worked, and we'll take a break for 10 minutes. It's 121, chapter 8A.